Here's an example of calculating magnetic forces on current-carrying wires. We don't have simply a straight wire. So I have this region of magnetic field here given in green. It's a square of side A, and we'll say A is equal to 40 centimeters, and the magnetic field, B, has a magnitude of 0.2 Tesla. And we can see from the dots that this is out of the page. So we also know there's a current then through this wire. This current is going in this direction, and we're say the current now is 3 amps. We want to know the total force, the magnitude and the direction of force on this wire. Before we go any further, let's get a coordinate system here. We're going to say this is the positive x, we'll say up is the positive y. Okay, so I got a picture, I've got a coordinate system. I've sort of listed the things that I know. What do I want to know? Magnitude and direction of net force. All right. So even though the total line itself, the total wire is not straight, I can break it up into components. And so I'll want to do that. We can look at here's a component, which, and then there's a vertical, sort of a vertical component to a wire, and then a second horizontal component. I'm going to call this vertical part, I call this length 1, and then this first horizontal I'll call length 2, and this second horizontal I'll call length 3. So I'm going to deal with the vertical part first, and then deal with the 2 horizontal parts. Okay, so at the vertical point, I want to calculate the force on this segment of wire. Okay, so that force then is equal to the current through that wire times this L1 vector across the magnetic field. This L1 vector is the length of the straight wire segment, and that's the magnitude of the vector, and the direction of the vector is in the direction of current flow. Okay, so this then is equal to, and then if I, to do the cross product, I need the right-hand rule. Okay, so if I take my right hand and point it down in the direction of the current, and then flip my fingers up out of the page, I find my thumb is pointing in the negative x direction. So negative x. So down and then up out of the page, my thumb is pointing to the left. And so verify yourself that that's true. I can't show you my hands. But then, and they're at right angles. And so we just have the magnitudes. So we have magnitude of the current, the length of that wire segment, the magnitude of the magnetic field, and to the left would be in the negative I hat direction. So this force is negative L1 IB I hat. Okay. So next, let's look at the horizontal part. Now, if I were familiar with these things, as I am, I would say, you know, this L2 and L3 combined is the same as a single horizontal wire that goes all the way across with a length A. And I might just calculate one, but that's okay. Let's not do that. Let's do both of them separately and confirm to ourselves that that's true. I mean, we're still new to calculating these sorts of problems. So we have the force on this segment of current here up front is the current through it times that L2 vector across the magnetic field. L2 vector is the length of the wire segment. That's the magnitude. The direction is in the direction of current flow. Okay, so it's also perpendicular to the field, which is great. That just gives us the magnitudes of the 2 vector. Now we need the direction, which is then given by the right-hand rule. So here, the first vector is going to the right, And then if I flip then my hands out of the page, I'm going to get my thumb pointing down. And so the resulting direction is negative j hat, so the force of this component is negative L2I B j hat. Now if we do the same thing with 3, F3 is the current times the L3 vector cross B. Note we have the same situation again and the same orientation. Current is going to the right. I flip my hands out and I get my thumb pointing down. And so negative j hat, and so negative the resulting force on the third component, L3 IBJ. Okay, so now if I go ahead and calculate these two F2 times F3, I get IB negative, of course, L2 plus L3J, and I can identify from my figure that L2 plus L3 is just A, so I have negative A I B J, which is just what we sort of anticipated from the beginning. The sum of these two segments is equal to the force on a single line that just went horizontally all across the region of magnetic field. All right. So now we have the forces on all the different line segments, and now it's just a matter of summing all the forces. So the net force then is negative L1 IB I hat, remember that was here, minus A I B J hat. Notice two things. First of all, we have to keep everything in component form. We have to make sure everything's a vector. Also, I'm not plugging in numbers until the very end so I can simplify my calculation, try to understand what's going on, and also it saves problems with calculator error. It looks like I can factor out a factor of IB, current times magnetic field, which leaves me with negative L1 I hat minus A J hat. Okay, that's now really looks pretty simple. I can calculate the magnitude of this, and the magnitude is just, there's IB, this just factors out, times that the magnitude of this vector. And the magnitude of this vector is just L1 squared plus A squared. You see, by keeping it in terms of symbols instead of plugging in numbers, now I get a much simpler expression. I have to plug fewer numbers into my calculator, less chance of calculator error. All right, so we have the current, which we said, what did we say what the current was? Current was 3 amps. The magnetic field was 0.2 Tesla. And then L1 was, or A, I guess, L1, fine. You talked me into it. 0.15 squared, A plus 4 squared, and if I put that now into my calculator, I get 0.256 newtons. Okay? There's the magnitude of the force. How did we do it? I didn't have a straight wire, but I could break it up into straight wire segments. I could apply this relationship to each of the straight wire segments and then simply do the vector sum of all of the forces. Okay, we still need to know the direction, and you can't escape getting a new picture for this. I mean, there's just no excuse not to do it. So let's get a picture. So, where's the sign? What angle do we use? All of those questions disappear when you simply set up a new picture and then calculate these angles for basic trig rules. Okay, so where is this vector pointing, really? So it has some, well, let's see, hold on. Let me get a different color here. So here it's got a component in the negative x direction, which is IB times L1. L1's 0.15, so I could come over to some sort of IB 0.15 In the negative x direction, the y component is IB times A, which is 0.4 in the negative y direction. So down here we have 0.4 IB. So that gives me where this is. And then so there is the force vector, the resulting force vector. It's got two negative components, fine. And so now I want to find what direction it is. Just give me any appropriate angle. I can look for this one right here. Call this theta. So if I want to find that theta, I draw my right triangle, and I know the length of this side can be 0.15, and the length of this side can be 0.4. Do you see? I mean, I don't have to worry about the IB or anything like that. I'm just doing basic trigonometry. I know where the force is pointing, and I can create a right triangle where I know what the sides are, and then I can just go ahead and calculate that angle because I know that tangent of theta is the opposite over the adjacent, which is 0.4 over 0.15. And my calculator tells me that angle is 69.4 degrees. And I have to identify where. It's counterclockwise from negative x-axis. And now it could be that the problem asks for a specific axis, maybe clockwise from positive y or counterclockwise from positive x. Then you just have to add the appropriate 90, 80, 270 degrees, what have you. But to actually find the angle, there's simply no substitute to drawing your coordinate systems, finding where that vector is, drawing your right triangle, and coming up with your angles from basic trigonometry. You never have sign errors that way, and you always know exactly what angles you're talking about.